Here we have a question on chapter 12, the subsection being photoelectric effect. Let's have a look at the question. In an electronic circuit used to investigate photoelectric effect, the voltage is varied until the reading on the ammeter is 0. The stopping voltage that produces this reading is 1.4 volt. Here the stopping voltage Vs is given to be 1.4 volt. It is necessary for us to remember that stopping voltage is the voltage that is provided such that the electrons that are emitted during photoelectric effect are no longer capable of attaching themselves or moving themselves towards this plate or collecting at this plate. Question A dictates describe photoelectric effect. We describe photoelectric effect as that phenomenon which results in the emission of electrons from the surface of a metal when light or photons specifically of a particular minimum frequency known as the threshold frequency are incident on the metal surface. Photoelectric effect is not the only phenomenon, however, where electrons are liberated from the surface. There are also other phenomena such as thermionic effect and photovoltaic effect. Moving on to part B, state the maximum velocity of the maximum velocity of the photoelectrons is 700 km per second. So here the velocity V, denoted by the small letter v, is 700 km per second, which can be approximated to 7 into 10 to the power of 5 meter per second in SI unit. Here we understand that when electrons are emitted, they contain a minimum amount of kinetic energy, and this kinetic energy propels or pushes the electrons which are emitted towards this plate, that is a plate on the left named A, to the plate on the right, which is B. Here we also notice that a stopping voltage is applied to prevent the electrons from collecting at this point. Hence, we also understand from the given scenario and from the definition of stopping voltage that the energy supplied due to the stopping voltage Vs is equivalent to the kinetic energy of the electrons. Energy supplied from the stopping voltage Vs can also be defined as work done by the voltage, which is equivalent to the kinetic energy of the electrons. Work done from the voltage is Q into Vs. This is equivalent to half mv square. Here Q stands for the charge of each electron, which is taken from the data booklet to be approximately 1.6 into 10 to the power of minus 19 coulomb in magnitude. Vs is the stopping voltage given in the question. M is mass of each electron, again approximated and taken from the data booklet to be 9.11 into 10 to the power of minus 31 kilogram. When substituted, we get the value of velocity V to be approximately equal to 7 into 10 to the power of 5 meter per second, proving answer B. Moving on to the last part, the photoelectrons are emitted from a sodium surface. Sodium has a work function of 2.3 electron volt. Calculate the wavelength of the radiation incident on the sodium. State an appropriate unit for your answer. Here we understand that work function is the minimum energy that is provided for the photoelectrons to be emitted. Here the work function denoted by phi naught is given to be 2.3 electron volt. The total energy supplied, E, is equivalent to the minimum energy that has to be supplied for photoelectric effect to occur, which is nothing but the work function phi naught plus the 1.4 electron volt of energy that is supplied through the stopping potential. Here 1.4 volt is the voltage that is supplied. The energy that is supplied is calculated as Q into V, and when converted in electron volt from the standard unit, which is joules, we get the value to be exactly equal to 1.4 electron volt. Hence, the value 1.4 electron volt is taken. The total energy becomes equivalent to 3.7 electron volt, and this is equivalent to the energy of the photon, which is found out using the equation h c divided by lambda. Here h is again Planck's constant, which from the data booklet again is given to be 6.626 into 10 to the power of minus 34 joule second. C is the speed of light, again from the data booklet, given to be 3 into 10 to the power of 8 meter per second. All these values, when substituted, give us the value of wavelength to be approximately equal to 340 into 10 to the power of minus 9 meters, which is written as 340 nanometer.